back. I hope you're having a good time at the online conference today. So, my name is Randall Hunt. I'm a software engineer and developer evangelist here at Amazon Web Services, and I've got some slides on screen. Twitch is not typically the place where we show slides, but I thought given the nature of what we're trying to build, it might make sense to go with a little bit of prepared work. Now, the way that this works is there are, there's chat. So you can chat with me, you can send things live from the chat here, and I will try to answer those questions. So FireB675, hello to you as well. And Alistair Plays says, Wat, it's 1 a.m. It is indeed 1 a.m. And this session is going to be a lot of fun because it's 1 a.m. That said, I think this conference, this Innovate conference, this online conference, it's a free conference that everyone can attend. It's going very well. I hope you're all enjoying it. I hope you're checking out some of the sessions. I hope you checked out Dr. Werner Vogel's session. And I think with that, we are ready to get started. So this is me. Like I said, I'm just a technical evangelist at AWS. I write a bunch of demos and kind of fun stuff on top of AWS. This is my real official badge photo. Don't know exactly how that happened. And almost everything we're going to be doing today is in Python. If you want to see some non-Python code, you got to go find another streamer. So this is what we're building. And if you were in the previous session, you've probably already seen this. So the way that this works is we build a Twitter bot that tries to identify where in the world a picture was taken based solely on the pixels in the image. So it's not using any of the EXIF data, which is what people typically use to populate an image with latitude and longitude. This is actually just taking the pixels that make up the image and determining where exactly they could correspond to in a graph. And there's some kind of cool magic for how this happens. So before we jump into the magic, I'm going to cover the architecture. Now, I want you to ignore the right half of the screen right now, or maybe it's the left half, depending on how Twitch has flipped things. And I want you to focus instead on this half, this serverless half. So what's happening is Twitter has an API, and this is a webhooks API. And the way that this works is we authenticate a URL of our choice with Twitter, and we say, hey, Twitter, when an action happens, we want you to call out to that URL with a payload, and we want you to invoke this Lambda function. And a Lambda function is really just a very simple serverless function that contains some code and responds to this incoming request. And there's some more things we can talk about with Lambda. Now, in the session earlier today, we covered how to build that serverless side, but we didn't quite finish it. So my plan is to kind of come back to the serverless side of things, finish building all of that, and then jump into the Amazon SageMaker side of things. The SageMaker side of things is a machine learning service that we have at AWS that kind of lets us build and host and train our own models. And if you saw Julian Simone's talk from earlier today, you would have learned how to build and train your own model on SageMaker. Now, I'm going to be using the US West 2 region, and I'm going to hop over to some code now. So if we go over here to the Lambda function, this is what we built in the previous session. Now, I'm going to just briefly adjust the chroma on my screen here, just because it's weird to have my face kind of half in, half out. Hopefully that's a little bit better. And what I'm going to do is go over this code that we've already created. So the way that Twitter works, as I said before, is you register a webhook. So you take, using their API, you take your secret key and your access token and all this good stuff, and where is this? You can grab those credentials from Secrets Manager, which is where we are storing them, and then you sign the incoming request. So if Twitter is making a GET request to our webhook, we sign that request and we return the signed token so that Twitter can verify we are indeed the ones who are making this request and we are indeed hosting that endpoint. Now, the way that this works and the kind of management section of this is, in my opinion, a little bit more important and interesting than is the CRC and security portion of this. But security is important, and I think it's worth covering exactly what's happening here very, very quickly. So hopping into this very briefly, I'm just going to go over what exactly we're doing. Essentially, we're creating an HMAC, which is a type of signature based on the consumer secret of our application, which is something that Twitter will give us when we register our application, and based on the incoming CRC token that we get. And then we're SHA-256 encoding it, and we are basically creating a JSON string that contains response token and SHA-256. Now, when it comes to verifying the incoming requests, what we're doing is we're collecting a CRC from the incoming event, and this will be a Lambda proxy invocation, and we're grabbing this X-Twitter webhook signature header, which contains our CRC. We're basically doing the same process here of grabbing the CRC, but in reverse. What we're doing is we're saying create this our own CRC based on the body of the request, and then take out the CRC that was given to us from Twitter, take out the first 7 characters. So those first 7 characters, they correspond to SHA-256 equals, and then return whether or not the calculated CRC, the one that we just calculated, this h.digest, and the CRC that we've decoded from this web header are the same. And if they're not the same, then that request is not really from Twitter, and we know that it's not really from Twitter. So then we kind of get into what this Lambda request is supposed to do. And if we look at this code, you can see if the path is not webhook, then we just want to return a 404. If the event is HTTP method get, then we want to get the CRC. And if the CRC isn't there, that means it's not a valid request. But if it is there, then we want to sign the CRC and return that. Now, the second part of what we have to do here is deal with the chance that the incoming request from Twitter is not valid, or that it's not really from Twitter. Somebody else is trying to pretend to be Twitter. This is really easy with this verify request method that we created. So we just say, if not, verify request event context. We want to, maybe print unable to verify CRC, and just for debugging purposes while we're getting started here. And we want to say status code 400, and body is going to be bad CRC. Now, with that, we don't actually have to do much else. We really just have the meat of our function now, because if all of this is working, if this request is valid, then all of this stuff is just preamble. So we could even kind of wrap a lot of this into its own method if we wanted, which was, is valid request. And we could return a payload from this. So we could say event context. We could say all of this, move all of this into here. And you guys can see everything okay, right? Do I need to make it any bigger or move it around on the screen at all? Let me know. I have a big microphone in the way of my screen here, so I can only see the left half of it. So what we want to do in this case is we kind of want to return FOSS and then this payload. So we want to return a tuple, and then we want to return false. And false needs to be capitalized. Return that. And then we can return true on this one since this is a valid request. Actually, we don't even need to do this. We could just add some additional logic in the main Lambda function. So let's do that instead. So we're going to do it like this. What we're going to do is say if is valid request, or so we'll say valid equals is valid request event context if valid status code else return, we'll just return an empty body. So we'll just have one last little section over here where we say status code is 200. And we're just going to say response. So status code is going to be 200 and body will be empty. So response for is valid request is going to become if valid status code equals is greater than or is greater than or equal to 400, then we return the response, else we can start doing some work. So that's basically saying if our status code is anything other than A-OK, if it's 400 or above, any kind of 400, then we just want to return this is valid request response. So maybe we should have rewritten this verify request context. Change valid to response on line 51. Yes, good call, good call. Nice catch, Gabe Hollum. Oh, hey, hi Gabe. So there we go. Lambda handler event context return response. Now this is where, I mean, we can save this and we can test it very quickly. So we can hop back over to API gateway. We can look at this method. We've done a proxy invocation here, and we can go and we can click test on this method, and we'll just make a quick GET request, test this, and of course we got an internal server error. And we have an attribution error for get CRC token on line 51. Response is valid request event context. In line 31, so we didn't respond correctly here. So line 31 should be doing more. So we should be returning CRC not provided or invalid. That is not what we are doing. Let me see what exactly is happening here. If event.getPath/webhook. We're invoking this. Sorry, I've got a big microphone in my way. Error message, none type object has no attribute get. So the event that we're passing in has no attribute get. So CRC equals event dot get query string parameters dot get CRC token. Yeah, I think we've got this path wrong, but I don't think that's what's causing it, just because it is getting past that section. So if we hop over here and we look at this, maybe we can go look at it in a little bit easier place. We can hop over into monitoring and we can say view the logs in CloudWatch. This will take just a moment to load. Can open up the stream, and it seems like on line 31, none type object has no attribute get. So our event is not being populated for some reason. Very confused. Let's try a post really fast. I think we're gonna run into the same issue. It's very strange. Let's hop back over into the code. And let's just step through it. So when something like this goes wrong, what I like to do is I just kind of go through the path that my code is tracing. So we're definitely hitting this function. So we know that we're getting there. And so maybe I think we just need to say item is going to be an empty dictionary. So then we say item, or so we'll say event equals event.get query string parameters, and then we want to return an empty dictionary if that's not the case, and then we want to say get, so we're going to say crc equals, and then we want to say get crc token. So we've done that. Now our crc should be none. So if not crc, print no crc. No crc. So that is solid, and we returned that. So we're definitely hitting that. Let me just try something really fast. If we change this to be return empty string, does the same code work? It does. So let's just change this to return empty string and see what happens. We'll hop back over into API Gateway, and we will say test this again. I'm just trying to get this to return a 400 essentially. Rather strange indeed. I'm probably just doing something foolish. Let's see. We have none type object has no attributes get error type. Stack trace from line 51. Response is valid request event context. Line 31 is valid request crc equals event get query string parameters. So it's definitely invoking the right version. What could be happening is query string parameters could be not empty, in which case when we call get crc, but if it's not empty, it would still be a dictionary, in which case we would. So Gabe has the suggestion of splitting this into two different calls, so we're going to do that. Query string is going to be event.get query string parameters. Make an empty dictionary there. And then crc is going to be event.get crc token. And then we'll say print query string format query string, And we'll do the same thing here. We'll say CRC. I'm going to print this CRC. It's going to be query string. So let's test this again over on the API gateway side. And of course, we'll get the same error. And hopefully it'll at least be a different line. So it's that the event is not being populated somehow. Because it's line 32 this time. So why is the event not being populated? No, the pair programming is very much appreciated. Thank you. So let's hop over to line 32. Query string parameters. So I think what we need to do really is this. Save this whole shindig. And then hop back over here, check out these logs. It's definitely on query string.get. So how is this returning a none type? Very, very confused. Wait, is there a typo? We're definitely passing this in. Event, context. Wait, is there really a typo somewhere? Okay. So if you guys have never seen me live stream before, I typically go into these projects with very little preparation just because I think it demonstrates a little bit better what the actual process of programming is like. Because if you already have everything copy pasted, and I've built this before, so I know the general structure and flow of everything. But even if it's set to none type, it should still, I mean, that's a problem in my condition at that point. So if query string is none, then query string needs to be equal to empty dictionary. That's the only thing I can think of doing. So we'll save this absurd condition. Oh, yeah. So who was that suggested that? Chaplepi says maybe query string actually exists and is set to none. And that is, of course, exactly what it was. So now that we've done this, we can start making progress again. Good call. Good call. That will never actually happen in production. Because if there is no query string on the request, then the API gateway is not going to create that method. So that is a weird thing that I've never run into before. I'm going to remove these print statements just because there's no reason to kind of populate our logs with them. And welcome, Hines. Thanks for joining. So now we have the kind of meat of our request here. So if their code is greater than 400, we're going to return whatever bad response we got. Otherwise, our response is ready to be populated with some kind of, whatever Twitter is sending us. So let's go look and see what one of these payloads looks like. And these are going to be the account activity API data objects. And we're primarily going to be interested in these tweet create events. So this is what a tweet create event looks like. It's going to be some JSON, and it's going to be for user ID, tweet creator, and then a tweet object. So what does a tweet object look like? Tweet object. Wonderful. That is not at all helpful. Thank you. This is all in Python. So I shouldn't be I shouldn't be so hard on Twitter because they have actually made this much better than it was originally, but there's still a long way to go. But I am thankful for the people at Twitter who have made this. You know, previously there were no payload examples at all, so you just kind of had to guesstimate what exactly was happening. So, you know, a favorite event or a follow event, any of these sorts of things, you just had to wait for one of those events to actually happen in production in order to figure out what at all was going to happen. And Foshi asks if we still need, or Fashi asks if we still need the empty dictionary here in query string. And we don't really. So we can get rid of that. So, or do we? Get's gonna return none. Yeah. So we don't need that. And Chobo Chung is asking if you want to learn how to code, can anybody give me advice? I'd strongly suggest checking out Codecademy if you're looking to learn some JavaScript, and then there are tons of other really cool things to check out, tons of great resources online, things like Code Combat and all that good stuff. So we are certain at this point that our requests are secure. We have done everything we need to make that happen. And now we want to make sure that these tweet create events that are coming in, we can parse them. So the easiest way to do this is going to be to say print, or sorry, have I imported JSON already? Import JSON, yeah, I've got that. The easiest way to do this is actually going to be to say for event in Twitter events .get tweet create events, and then we'll return an empty array if nothing was there. We just want to say I guess what we really want to do is we want to create this like Twitter events construct from the incoming data. So we'll say json.loads event body, and then we can do whatever we want with each one of these events. So I think for now we could just say, you know, print the event, you know, log it out, and then we can just return that response object from before. We don't really need to do anything, and that's a good start. And then we can go and actually register this webhook. So everything is up and running. This is deployed into prod. So if we go back to here, we've created this little API gateway, and we've got it running in prod here. And all we need to do is basically just tell it to invoke this endpoint. So I mean, that's it. That's the entirety of how a webhook works in Twitter. You know, if you wanted to see exactly what the code is doing on the machine learning side, we can jump into that next. But and some people are asking, what exactly are we coding here? So I'm going to go back very briefly to the architecture. Basically, we have Twitter coming in and talking to API gateway over webhook, invoking Lambda function. That Lambda function is going to read the incoming tweet and respond to it. And what this looks like at the core, when we get to it, what this looks like, oops, sorry, the wrong tab here. What this looks like is, if my internet speeds up at all, sorry, I think my computer's about to take off. It's like, I can hear the fans running. So this is a picture, I guess, somebody is taking of the Golden Gate Bridge, and it's correctly predicting that it's in San Francisco. So that's the machine learning side of what we're building. And I'm just going to show you now what that machine learning side is about, because rather than replacing the currently working webhook of WhereML, I'm just going to show you the code that we use to make it work. So what we do is we have something called Boto3, and I'm not going to make this perfect. I'm just going to say normally your imports should be at the top, but I'm just going to kind of show them down here so that they all fit on one screen. So we're going to say SageMaker equals boto3.client SageMaker. And then we say we want to basically invoke this SageMaker endpoint. So we're going to say SageMaker.invoke endpoint. And in this case, it's just going to be predict places. And I haven't showed you how to make this yet, so don't worry if you haven't seen this endpoint. And then I guess I need to actually pass in the keyword arguments here. Endpoint name equals predict places, and the body is going to be JSON, and we're going to take that tweet event that we got, and we're going to encode it by saying URL is going to be I've got to get to the media somewhere. So I think what we need to do is we need to find the media of the request. So in order to get that, we're going to have to look at the tweet object. So what we need is we need the JSON tweet object example. So hopefully this will give us some idea of what this looks like. Media is going to be one of the things that we're looking at. So is it going to be in entities? So it'll be in entities. So I'm going to move this to one side, and then I'm going to grab this off on the other side, and it'll basically be we're going to pass in the URL of the media. So we're going to say, instead of this, we can just say for tweet. No, it's going to be an event because it's not just going to be tweets. So we're going to say for event entities media, and we're just going to hard code grab the first piece of media, and we're going to go URL. But I think that's what we're going to go. But we need to look and see what exactly media looks like. So we need to see what a media object looks like. Media object, here we go. So it looks like there are a couple different kinds of URLs here. If you see my head moving around a lot, it's that I've got a big microphone kind of in the way of my screen here, so I'm having to kind of dodge around to see what exactly is happening. So maybe I want media URL HTTPS. That's probably what I want. And I think with that, we'll have at least the first part of what we want to pass in. So we'll go back over here, and we'll say this is going to be the maximum number of predictions that we want to generate. And in this case, I'm just going to say 3. So at this point, this is the majority of what's happening. And all of the magic is kind of happening in this SageMaker invoke endpoint section. So I think that's the end of what we really need to talk about on the serverless side. Maybe we do something else afterwards where we go Twitter API post update, and then we build the status. We build the content of the tweet that we want to reply with, but that's not too hard. So I've done that in another repo that everyone is welcome to check out. Now I'd like to jump over into the SageMaker side of things. So I'm going to open Amazon SageMaker. And I'm going to show you what one of these models looks like. So this is a model. And a model is maybe not the best name for exactly what is happening here. Is the invoke endpoint bracket closed? Let me double check that. Well, I'm not even doing that section anymore, but it's fine. I'll show you the real invocation later if anybody's interested. That invocation was more just kind of educational. So what is happening here is I've provided a Docker container for my endpoint. Now, when I say I provided a Docker container, that is a Flask application, very, very simple, that is just going through and loading a model that's been provided for me by SageMaker. So you can see what this model is. It's called LocationNet. So here's a good example of it. There's a whole blog post about this. And the content of this is available right here in LocationNet. Where is this model? So this is just, I think it's like a 100 megabyte or 200 megabyte model. It's really, really simple. And I'm going to tell you a little bit more about it now. So we're going to hop over into the way that all of this works, and I'll try and cover some of that. So I'm going to skip a bunch of slides. I'm going to skip some of the foundational parts of the way these things work. So the problem that we're trying to solve is identifying where in the world different images are, not from the EXIF data in them. So let's imagine a scenario where we don't have the EXIF data available to us, but we still want to guess where something was taken. So that's the frame of a problem that we've started now. Now we have the data collection part. We have something called the Multimedia Commons dataset, which is a couple hundred, it's about 30-40 million different geotagged images. Now, among those geotagged images is the Multimedia Commons dataset actually contains 100 million images and a couple 100,000 videos. And it's just a ton of multimedia that you can use in any kind of machine learning process. And of those 100 million, only about 33 million contain geotagged information. So we're extracting that geotagged information from that entire set of images, several hundred terabytes, and collecting that, keeping that kind of separate. But paired with the file name and all that good stuff, we are kind of cleaning the data. We can do any sort of visualization we need. That visualization that I'm talking about, I'll show you as part of the next step, and it's really just helping you understand how your data is distributed. And the reason you perform that visualization step, and you typically do this on a SageMaker notebook instance because it can be quite compute intensive, and the notebook instance typically has more available compute power than what your laptop may have, or even more space than what your laptop may have. The reason that you do this visualization section is it helps reveal biases in your data. It helps you reveal any kind of techniques you might need to implement in order to change around what exactly is happening in the model. So then you train the model, and the training section is pretty straightforward in a system like ResNet, which is the type of model that we are using here, which is an image classification model. So you're hearing the term ResNet. When you think ResNet, just think this is an image classification model. It's just a series of different layers that perform different things on the incoming pixels of the image and try and tell me what I should expect as output. So we don't really have to worry about feature engineering at this point, but we do need to worry about model training and parameter tuning, and then model evaluation. Now, SageMaker takes care of pretty much all of these components, but you do need to write code for the data visualization and for the that's it really. Those are the only real parts you have to write code for. And for, I guess, the data preparation and cleaning. Now, after that, you get into the point where you want to host and run that model for real-time inferences for your customers or for your internal projects. Now, SageMaker makes this quite easy because I can just say, hey, take the model that you just trained and create an HTTPS interface for me to invoke this. And I can actually have different kinds of things called model variants that I use to invoke many models simultaneously, or to invoke one model sometimes and another model sometimes. So 90% of my traffic goes to one model, 10% goes to another model, all that good stuff. So this is based on work. Sorry. This is based on work by Jae-Young Choi and others at the International Computer Science Institute and the University of Berkeley. And we supported the development of this. And I think the original invocation of this kind of, hey, we can identify where in the world this pictures are taken, was actually done by Wayland et al. From Google in a paper called Planet. Now, Planet, the resulting model was like 20 gigs. It was huge, which means you needed a really beefy server to host it. It's not something that you could have put in a Lambda function, and it's not even something that you could have really hosted without having 20 gigs of RAM, because you needed fast access to that entire network in order to be able to successfully predict the output. So what LocationNet did, as opposed to using this dense neural network architecture, is they just took a more common model topology called ResNet. And they took ResNet, they took Apache MXNet, and they pushed those 33.9 million geotagged images through a P216X large, which has a GPU on it, and they trained for 12 epochs over 9 days. Now, they took out that last layer, that classification layer of ResNet, and instead of classifying whether or not something was a microphone or a computer or a glass of water, they said, classify this as if it fits into one of these 15,000 cells. So they know from the training set where images should lie based on that EXIF data that's coming in. That's part of the training section. So they took that last layer and replaced it with a visualization that I'll show you shortly. Now, since this original release of the paper, we've actually been able to do a couple of things to improve the speed. So the first part is calculating this S2 spherical geometry subdivide is very, very compute intensive. If you think about it, you have to basically run a series of indexing operations across 33.9 million geographical coordinates. So you need all of those coordinates to be available in memory in order to form that index. So that takes a little while to run. And by parallelizing that process, you can get a little bit of a speed boost. So that was the first thing that I kind of did to make this model a little bit easier to run in the pre-processing step. Now, the second step that we did to make it a little bit easier to run was to switch from a P216X large and from a single machine into multiple machines and onto a P3 16X large. Now, the P3 has a much more powerful GPU and is capable of basically a teraflop plus of compute, which is absurd. It's a tremendous amount of power. And so you can take this 9 days down to 1 day or less, actually, for training. And if you're doing hyperparameter optimization on top of that, you can actually bring it down even further. So you can say, I want you to explore the entire solution space here from as many different spaces as possible, and I want you to run multiple jobs simultaneously. And then any job that isn't converging immediately, if our parameters are too far out of bounds, I want you to kill it off. So this is what the topology of that ResNet architecture looks like. I know this needs no explanation, right? So if you're seeing this and you're worried, you're like, machine learning is too complicated. If I had seen this the first time I had started doing machine learning, I would have freaked out. But all you need to think about when you hear ResNet is it's just a convolutional neural network architecture that has cheat codes built into it. So those cheat codes say, if the signal on one particular section of this image is strong enough, I actually want to skip a bunch of layers and go down to the next layer where that signal corresponds to. And that's a good way of thinking about ResNet. So this is that classification layer. Now this is taken from the Planet paper. And if I can just show you this, what's happening is, we're finding the locations where we have more pictures. So keep in mind, this data set, it came from Flickr. So places that have fast internet and places that have readier access to digital cameras and the ability to upload are going to have way, way more data than places that don't. So we don't even need to have cells in some parts of the Earth. I'm sorry to see that Greenland's not included. Greenland's very beautiful. Well, I mean, it's okay. And Iceland, you can see, is only a few cells. And then if you get into the South Pacific here, there's just really, in the Antarctic, there's really just very few places to put this data. So the way that this is built is it uses a concept called Hilbert curve. And this is a piece of fractal geometry that allows you to take a two-dimensional space and translate it into a one-dimensional space while preserving locality. And this is just not that important. It's just a way to think about, okay, wherever we are on this line, we know that the 2 points are close together if they're numerically close together, and it allows us to densely pack all of these different multi-scale cell regions. So there are pros and cons to this approach. The cons is that the performance for common objects, things like McDonald's signs or 7-Eleven signs, is kind of poor. And it's quite inaccurate in places that have only one giant partition. It's much more accurate in places with more partitions, which should be obvious from the architecture that we've described. But the pros are spectacular. It's less than 300 megabytes. It's got excellent, excellent performance for unique objects and landmarks. And it's quite fast in terms of inferences. So even on a T2 large, which is a fairly small instance, we can infer what exactly is happening quite quickly. So let's skip over a bunch of stuff here, hop back to the code. I don't think we're going to need the slides again. I'll make them available though. And I'm just going to show you what this Flask app looks like. So I'm just going to call this app.py, and I'm going to say, import Flask. We'll say from Flask import requests, and I'm going to need JSONify to JSONify. And then app equals Flask dot Flask. What did we say we were going to call this? Does anybody remember from the last session what we were going to call this? Was it like Innovate bot? Innovate bot. So Alistair Plays asked how that specific visualization was made. That was made using Matplotlib, if I remember correctly. In fact, I think it was made using a framework that's built on top of Matplotlib called Bokeh, or Bokeh. So there are only 3 things that we need to do in order to make the SageMaker bring your own algorithm work. So the way that this works is we say app.route/ping, and this ping needs to do a health check on how our app is performing. So we're going to say that our health is always great, so we're going to return an empty 200 OK, which is the best health check in the world. Obviously, the app is just fine. So we're going to say, and then we're going to create another route, which is going to be /invocations. Methods equals post. So this is going to take a post request. And then we're going to say invoke is going to be the name of this method. And we're going to grab our data, request.get JSON. And then we're going to say whether or not it's JSON, we want to make sure that we get this data, because sometimes you can submit to an endpoint, but you don't actually set the content type header. So the way that Flask works is when it's trying to figure out whether or not a request is JSON, it looks at the content type header. And if it's not application/JSON, it's not going to work. It's just going to give up and throw an error. But we want to force it to make sure that it's JSON or fail. So then we're going to say predict. Oh, and I'm going to need to show you how the prediction works. But basically, we're going to call out to the model. We're going to say download and predict. And we're going to grab the URL. And we're going to say integer data.get max predictions if it's in there, or just 3 as the default if it's not in there. And then if data.get, this doesn't really matter actually. We don't need to do this part. We can just return JSONify result. Yeah. So and then we just say, so that we can test this locally, we just say if name equals main, then 1 2 3 4 app.run host equals, and we're going to say 0.0.0, so I don't have to tell it to talk to localhost. We'll leave debug as true for now, and we'll say the port is going to be equal to 8080 because that is what SageMaker is expecting this app to run on. So that is, let's look again, about 18 lines of code, and that is how we run so 19 lines of code. That is how we run our entire little production endpoint. And all the CloudWatch stuff, all of the good things that come in will just be brought in for us. So the next thing that we need to do is we need to talk about how we actually run the prediction. So rather than recreating all of this, since we've already done it in a previous session, I'm just going to load that one in and walk you through it, given the time constraint that we have. And so we're going to import Apache MXNet, and then SageMaker will auto-populate for me the model path and the model name. But just in case I wanted to run this locally, let me see, stat/opt/model. Yeah, okay, so I do have this locally as well. Just in case I wanted to run this locally, I've pre-populated those values. So what we do is we load the model, which is really just the combination of model path plus model name. A more correct way of doing this would really be os.path.join, but we don't need to worry about that right now. And we're going to load the 12th epoch of that model, and we're going to bind that model to the CPU. And we are going to basically create a description of the data layer, which is really just 224 pixels by 224 pixels RGB. So this is just a description of the shape of the input data. And then we're going to say for training is going to be false. And then we set the parameters that we also loaded from those JSON files. Now, this mean RGB section is worth talking about. What we're doing here is we're meaning the image. We're kind of bringing the color value down to something that is less extreme, because when we have these outliers in our data, it means any image that's like all yellow is going to get forced into one cell, most likely, or any image that's all black is going to get forced into one cell. By mellowing out the colors and making the variance between them smaller, we actually get better results in the long run. Now, there are ways, of course, to get around that, but this is an example of something I would call feature engineering, where you're meaning the image, and it's really common in image classification frameworks. So then we create a batch, which is just named tuple, and we load in this grids.txt file. That grids.txt file is this thing. So where were we? This is the grids.txt files. It's just telling you where the different cells are. So we load in that grids.txt file, we download the image, and then we pre-process the image, It looks like this is doing a lot of complicated stuff. All it's doing is cropping the image and then adding in the mean. Then we call mod.forward. So mod, if you guys don't remember, is this section right here. This was the module that we've created. So we're calling mod.forward. That means forward propagate the 224 pixels by 224 pixels that I have in my batch. I want you to push it through the network, and I want you to tell me what the result is. Now, the result of a ResNet model is going to be whatever the size of your classification layer is. So that classification layer, that ResNet 101 classification layer, is going to be 15,527 different answers. So what we're going to do is we're going to tell NumPy to sort those answers by the probability. And then we're just going to return the top however many items we wanted to return. And then we have a couple of different useful methods. And I added this in wrench method a while back just to see if there was anything we could do to emojify the data or something like that, but there's no reason to do that. So let's try to run this. If someone has a suggestion for an image that we could pass into this, like what's a location in the world that you are interested in submitting a request for? Anything at all. While I'm waiting for people to answer, I'm just going to import SageMaker really fast. Sorry, I'm going to say import Boto3 SageMaker equals Boto3.client SageMaker, and I'm going to say do region name equals US West 2, and then we're going to say SageMaker.invoke endpoint. SageMaker.invoke, come on, invoke. Huh. Normally this will give me the right thing. I don't know what's going on here. Come on. What even? I have no idea why that's not tab completing, but not to worry, we can just do this manually. Invoke endpoint, and we'll just say endpoint name. And I saw somebody say that use the Taj Mahal, so we're going to do that. And I only have 2 minutes left, so I'm going to do this really, really quickly. Endpoint name is going to be predict. What is the name of this endpoint? V2. And the body is going to be JSON dump string URL of whatever we can find. So I'm going to Google the Taj Mahal, and I'm going to just grab. Yeah, unfortunately, we cannot allow people to post links. I'm sorry about that, but thank you. I'm going to look for some images of the Taj Mahal, and I'm just going to submit those really fast. So take this image. Copy image address. I think this is the image. So I'm going to take that image and I'm going to post it, and we'll see if we get a result. Something is very wrong with this kernel. I forgot. Has no attribute invoke endpoint. Oh, you know what it is? I need to do SageMaker.runtime. Or I think it might be runtime.SageMaker. So that was our issue. And then this is the request that we got back. So I'm actually just going to say that the response is equal to the last result that we got. And then if we look at response, sorry, body.read, we got back the following URLs. So I won't be able to read that again. So why don't I just do body, sorry, .read, and I know Gabe is ready and trying to go, but I just want to see if we actually managed to get this, the response right here. So I'm going to say json.loads. And let's just throw this on Google Maps really fast and see what happens. Those are the two responses that we got. So that looks pretty darn close to the Taj Mahal to me. Looks about right. So you can see we could even pass in and we could say, you know, we want more predictions. There's another building actually in Delhi that looks not dissimilar to the Taj Mahal. I mean, it's a totally different building, but it doesn't look too different. And I wonder if we went to max predictions, if it might give us a location near Delhi. So if I go to like 450 predictions, we can see how many predictions we'll get here. And I'm sure one of these will be off by a bit. So this one might be Delhi. The 77 instead of. Yes, the Red Fort. Or I think the Red Fort is in Jaipur. If I mean, I don't remember. It's been a long time since I've been back there. But is this the Red Fort? No, I don't think it is. So you can see that there's, you know, it's not perfect. It's deep learning. It does the best. It tries what it can do. But thank you for that suggestion for the Taj Mahal. I think that was a cool, unique kind of landmark. With that said, we are out of time for today. But I promise all the resources that you just saw are available for you. So you don't have to worry. I'll make all of this code available. I'll share it with everybody. But if you stay tuned on Twitch, I'm gonna go offline in just a second. But if you stay tuned, my colleague Gabe is going to be up next talking about AppSync and a couple of other things. So I hope you'll stay tuned, and Abe will be on in maybe 2 or 3 minutes. Thank you all for joining. I am going to go grab some sleep because it's 11 p.m. here in Los Angeles. Good night, everybody.